Okay, we're talking about section 1.4 now, and these are our quadratic equations. We know they're quadratics whenever there's the largest exponent is to the second power, x squared. Those are always quadratics. So everything in section 1.4 will be a quadratic. We have actually 4 methods for solving a quadratic, whereas in the earlier sections for linear equations, we just had one method. We undid what was done to the variable, worked our way backwards kind of to unravel all the steps to get to the x. But not so with other types of equations. So with quadratics, the method is, well, the first method I think of is factoring. If you can factor the equation, you can solve it by the zero factor property. Then there is the square root property. And then, which is a way we could solve this one, we're gonna start. And it only works if you have something squared equals a constant or some quantity. So you can work backwards by simply square rooting both sides. And then there's completing the square. And then lastly, the quadratic formula, which works for any equations. We could even use the quadratic formula on this equation, although it would be a lot of extra steps for something that can be worked an easier method. But anyway, if it's just x squared and we square root, those two operations cancel each other out. But what you do to one side, you have to do to the other side. So when we square root 484, I don't know what that is. I'm going to see if it comes out evenly and punch that on my calculator, and it does. That is 22. Now, an extra detail is when you take the square root, you have to account for the positive and the negative solution. So in the original equation, it's saying what squared equals 484. So positive 22 squared would be 484, as well as negative 22 squared would be 484. So there's a positive and a negative solution. You'll find that's true. Quadratics, in all quadratics, you have up to 2 solutions. So you should expect 2 solutions along this section. The only exception to that rule is if you were saying like x squared equals 0, there's not a plus and minus of 0, or if you have a repeated solution, sometimes it's the same solution just repeated. But all other times you should expect 2 unique solutions to quadratic equations. On the next one, we can use this square root property as well by throwing the 7 to the other side. Makes that a negative 7. And then we can square root both sides like we did before, canceling and leaving just an x to the first. Remember to say plus minus square root of negative 7. Now we should always reduce. If there's a negative under the radical, that comes out as an I. So plus and minus I radical 7. And you can put the I in the front or the back. Does not matter. Just don't forget that little plus minus. Next one is similar. When we square root each side, the square and root cancel together, bring out the, you say plus minus of the other side, and then we simplify. So one thing for sure, we can bring out the negative under the radical. That's the square root of negative 1, which is always an I. And then the square root of 175 reduces. 25 goes into that, and 25 is a per square. That'll reduce down a little bit. And let's see, 25 times is that 75. So the square root of 25 is 5. We've got a 7 left in the radical. And then don't forget your I. It can be at the end or between, anywhere really, as long as it's not under the radical. It should be out, stand alone. Oh, and plus minus, about forgot that. It's easy to forget. All right, next example, square root each side brings out the x, plus minus square root of 32. No I on this one, but it does reduce. There is a perfect square of 16. 16 times 2 is 32. Then the square root of 16 comes out as a 4. The 2 stays in. Don't forget it's plus and minus. That's the exact solution. If you were to type on your calculator the square root of 32, let me see if we can do that. I don't know if you can see that. It's a decimal answer. It's an irrational number. We talked about irrational, rational numbers in the last section. So it's a long decimal. That's not going to be an exact answer for us when it's an irrational number, on these radicals where if it's not a perfect square, we're getting these irrational decimals. That means they never repeat, never terminate. So we will have to round if we were to write our answer in decimal form, and it's just not as perfect. So this is the exact answer, and then 5.6-ish would be an approximation. If you were asked to approximate what number that was, we use a squiggly line. So that means we've rounded. But normally the exact answer is the preferred answer. All right, now we'll go to another type of solving for quadratics. So the next set says solve using the zero factor property. That's just another way of saying see if these will factor. They're probably factorable. You can do the reverse of the factoring or the FOIL method. And you're going to work these puzzles backwards and think what multiplies to give me t squared on the first times first. So I need a t times t. Then you think about this last term. To get a positive 48, the signs have to be alike, to multiply and get positive 48. But since there's a negative in the middle, that clues me in that it was a negative times negative. Gives me a positive on the end, negative. You can make an anytime negative positive. It factors into a negative, negative, negative. And then I think about how I can multiply to be 48. There's lots of ways. 6 times 8, 12 times 4, 2 times 24, 1 times 48, and I'm probably forgetting one even at that. But so you can just trial and error until something works. But I do see ahead that 6 times 8 would be 48. And then when I FOIL my inner, negative 6t, and the outer times outer part, that's the two that will combo up to give you the middle term. That's how you figure that out. Sometimes you can foresee what needs to go there, and sometimes you just write different numbers down, use your pencil and eraser till you get the right combination. But that does give me negative 14 for my middle term. So first should be t squared as designed, and the last we designed to be this last number. So we're really just concerned with inner and outer multiplying and then adding to give me the right middle term. All right, so that is factorable. If it's factorable, it's saying this quantity times this quantity equals 0. If you've got something times something equals 0, then either that first something had to be 0 or this second something had to equal 0. So that's what the zero factor property says. If you got an A times B, two things multiplied together that equal 0, then either this A equals 0 or the B equals 0, or they were both 0. 0 times 0 equals 0. So when we factor, we just factor it out and then solve by setting each parenthesis or each quantity equal to 0, which will give me solutions of positive 6 and positive 8. And then you can check it out and see if that's the two values that solve this. Is 6 squared minus 14 times 6 plus 48 equal to 0? And punch that along. That's 36 minus 96. Let's see, that must be negative 48 plus 48. Yes, that works. Then check positive 8. 8 squared minus 14 times 8. And you can use your calculator and check these out. 8 squared minus 14 times 8 plus 48 equals 0. There it is. So it did work. So just a quick check on these. I'm kind of lazy about checking. I prefer algebra than do my arithmetic, but I encourage you to check, and especially if you're taking a test or quiz, and then you'll know. So both of those solve that original problem, and there are no other solutions. Since it's a second degree equation, it can have at most so the biggest exponent, that's called the derivative, tells you how many solutions to look for. So quadratics at most have 2 solutions. So I know to look no further. That's it and that's all. All right, let's do it again. This one's very similar. We got w's this time. W times w is w squared. Negative, negative, again, same sign situation. And this one will be a 4 times 3. And then setting each parenthesis or each factor equal to 0 by the zero factor property gives us a positive 4 and a positive 3. And again, you can check that out and see that it is so. Okay, we're going to move on. Let's see what's next. Let's use some more factoring. So the factoring gets a little tougher in the next few problems. Whenever you have a coefficient on your first term, that makes it much tougher. Even after all of these years of teaching algebra, these I have to think about. And I not always just recommend you just guess and check, just trial and error. There are other methods students use over the years. You may have learned a different method in high school or under a different teacher. You can YouTube videos of different ways to factor when the coefficient's not 1. That's what makes these tough. So I'm just a guessing checker. So I just write down 5y times 1y. That's my guess. There's not a lot of ways to multiply and get 5. 5 is a prime number, so it's just going to be 1 times 5 or 5 times 1. Then for 17, it's also a prime number, so there's not a lot of options here. I'm going to put the 17 here and the 1 here. 17 times 1 is 17. Now what about these signs? I have a new sign issue, but a negative and a negative. So the signs are going to be different. I know they're different because I have to, the last times last needs to be a negative number. So let's just see if this works. Remember, we're checking it by the FOIL method. So the first is y per the design. The last times the last, the L part, is negative 17, again, per design. What I really need to know is the outer, inner, do they give me the right middle number when I combine? So the inner term, that's positive 17y, and then the out multiplies to be negative 5y. That combines to be positive 12y. So I'm pretty close. I've got the right number anyway, but this one's negative, this one's positive. So my signs are messed up. I need to switch those out, recheck it. Now the 17 is the negative and the 5 is the positive, and it works. All right, so factor that away, then set each factor equal to 0, and then solve each part, and then check each part, right? The two solutions should check out, and then y is negative 1. All right. Then we're moving on to number 8 to the square root property. So and we did this one earlier, actually, it's showing back up again. If you have a quantity squared equals a constant, you can simply square root both sides to solve. Now you could have FOILed it out and got it in standard form and used a different method, but it's set up for the square root property. There, something squared equals a number. We can simply square root. So square and square root cancel each other out and bring out that 2x minus 1. We have to remember to say plus minus when we use this method of that square root. Square root of 30 doesn't reduce, right? It's not imaginary, and there's no perfect squares, like 16 doesn't go into 30, 4 doesn't go into 30, 9 doesn't. There's none of those perfect squares that will break it down. So we just leave it like it is, bring the 1 across the line, makes it a positive 1 plus and minus radical 30, and then divide by the 2. And that will be an acceptable way to leave that answer. If you remember on the last section, we had to pull the fractions apart and put it in a plus bi form. You do have to do that if you see an imaginary in your answer, but this is not imaginary. This is a real number, no square root of a negative, so we can leave it right like that. It does not reduce, and that is perfectly good. All right, what's next? Okay, number 10, I'm going to use this property again. Set up just like this one. This time we will get them to show up. For minus, so it is imaginary, and square root of 25 is typically all comes out of the radical. And then to finish the process of the 7 line. There is no fraction in this one, so we won't have to worry about what I mentioned on the last one. We won't have to pull this one apart. It's just find the way there's no fraction involved to split. All right, now, next one, we're going to force this one to look like the last problem. We're going to make it a perfect square so we can square root both sides. That's one way to solve, by completing the square. So we've got factoring so far, then we have the square root property. So our next method is this completing the square. So we're going to make this look like that. And there's a little process. We move this constant across the line. We have to have a 1 coefficient before we can proceed to step 2. And then we take half the middle term squared. Half the middle squared, which will be half of 4 is 2, then 2 squared is still 4. Just coincidence there. We'll add 4 to the left, add 4 to the right. That's called completing the square. When you do so, that guarantees this to factor x plus 2 times x plus 2 into a repeater. Check it out, FOIL that, and it does equal what we had. So then it becomes just like the one above. It's a something squared equals a constant, and we can solve by square rooting each side and proceeding from there. And then we'll throw the 2 across the line. And since there's no imaginary or radical, we can finish this. Negative 2 plus 6, let's see, that's workable, that's 4. And negative 2 minus 6, that's doable too, negative 8. So the 2 solutions. Since these worked out to be such nice rational solutions, that tells me it was factorable when you get rational, real solutions. So, okay, we'll pick that up on the next video.